Hello, everyone. I'll be talking about a small library that we've been building. Has nothing to do with zero knowledge proof itself, but hopefully it's something that'll show you how you can use zero knowledge proofs. Specifically, like how you can deal with large amounts of data that you would need to verify in a proof or need to work with in a proof. If you think of how like most zero knowledge proofs start out with is like you have some sort of Merkel tree and you need to make a proof about some attribute, a leaf in a tree in Zcash that is like your coins that you have, your commitment. Other in what we're doing, it's sort of data, large sets of data. Just a little bit of background information. So we built this at Centrifuge, where we are building a decentralized protocol for companies to interact. So this means they send invoices and purchase orders back and forth. And sort of the very basic protocol is that you have Alice and Bob. They exchange data off-chain. They sign each other's data, and then that data gets committed on-chain. And this is our Merkel Route. So when I talk about data, this is described in protobuf. Protobuf is a schema binary format that is developed by Google. They try to build something that was better than JSON or XML to build their APIs with. We're using that as a way to sort of have a very easy, highly efficient serializable data and data structure, and then a way to sort of construct a Merkel tree out of something that looks roughly like this. So what we do is we have, let me skip this. Instead of like using a Merkel tree to prove that a transaction is part of a set, we actually can make a statement about a certain, and in our case, not a transaction. We just talk about documents. So that a field is part of a certain document. So what we do is we take, and this is an example of an invoice. We take each and every field. We create a leaf for each field. We encode the name of the field. So the amount. With the value, and the salt, we hash that, and then that's our leaf. So at a later point in time, if you want to use this Merkel route to prove something about your off-chain document, what you do is you say, here's the label, the value, and the salt. You hash that together. You give your Merkel proof, and you can prove that basically this value is included in this set. This now makes it independent of the position in the tree. So instead of having to rely on, oh, give me the 5th leaf in the tree or the 10th leaf, all I need to care about is that the field has the correct prefix. And going back to this specification, so this is something that protobuf is giving us. They use sort of these field tags, so just an integer that you denominate, like describe your field with. So this is basically the prefix we use to encode the field value. So in our case, basically Alice and Bob, they send these documents back and forth. They manipulate them, they validate them. They both know how to encode or create this Merkel tree based on the schema that they have. And can then sign the Merkel route. And if I now have a signed Merkel route, I can give you, like if Alice has a signed Merkel route by Bob, she can make a claim that Bob agreed to, for example, the invoice amount being $1,500. So practical example, let's say I have an invoice that I want to insure, so I want to ensure that my goods will be safely delivered. I don't want to tell the insurance company what I'm selling to my buyer. I don't want to tell them I don't want to reveal any of that on chain. What I can do is I can use these Merkel proofs in a snark. Basically, the insurance provider would give me a snark that has their fee table encoded. I could give my private inputs. So the invoice amount is $1,000. It's the goods are a certain category. The delivery country is the UK, and therefore I should pay 1% insurance fee. I attach a payment to it, and by validating this snark and the payment, the insurance contract can basically say, can check the committed state on chain and say, yes, this was a valid, this is a valid fee that was paid. Therefore, the transaction is now insured. This invoice is now insured. All right. So this concludes sort of the quick introduction to the precise proofs library. It's on GitHub. There's a Go implementation of it. You can sort of play around with it, try to sort of build your own complex trees. So we support all sorts of different data types. You can have sort of just sets, embedded messages, and then just create proofs very easily and actually validate them both in the browser and in Solidity. That's it. Are there any questions?
Any questions?
How can you make sure that it's easy to verify the proofs in different contexts? Like, for example, with snarks, you wouldn't necessarily use the same hash function to build your tree.
Well, if you are doing this within the context of Ethereum, you're ultimately bound by what Ethereum has to offer. The library itself is not opinionated about what hash function you should use. So one thing you can do is actually you essentially always trust the signature, right? So as Alice and Bob create these trees and sign it, and one thing that we've been thinking of doing to optimize for both snarks and EVM verification, you can have you duplicate the tree once you hash it with Peterson hashes, and once you do it with SHA-256 or SHA-3. And so if you were to make a statement that is public, you can use sort of the SHA-3 branch of the tree, and otherwise you use the Peterson branch of the tree.
All right. Thank you very
Thank
much.
you.